are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about the structure and bonding. So, the contents for today's lecture is introductions about the bonding. So, we will discuss and then arrangements of atoms. So, there are two dimensional crystal structure, three dimensional crystal structure. So, these are the things will be discussed. Okay. And then we will discuss about a few examples of three dimensional crystals and at the same times planes in the crystals. So, crystallographic directions, reciprocal lattice, bonding in solids. So, these are the things we will discuss. So, when we talk about any nanomaterials or materials, so that is made of atoms and molecules. Okay, so that when it is prepared in nanoscales, that matters maybe in three different phase. So, that may be gas phase, liquid phase or solid phase, that depends upon the temperature and pressures at which that matters exist or we are dealing with that. So, depending upon that temperature pressures or both temperature pressures, that would change its particular phase from one particular state to another. So, let us say suppose you have a solid material. So, if you increase the temperature of that material, so it would change its phase from solid to with increasing temperatures. Let us say the solid is present at this stage and the temperature we are increasing. So, solid material. So, it would change its phase into the liquid phase. So, further if you increase temperatures, then it convert into vapor or gaseous states, and in vapors or liquid, if we increase its pressure, then it would change that liquid state, but it pressure will rise that particular state of temperature, that we can say compressible liquids. And at this stage when gas, liquid and solid, both three components both are present, solid, liquid or gas, that particular temperature we can say it is a triple points where three different phases coexist. So, at the same time, so when suppose we have a liquids, so it has liquid converted, if we further increase temperatures, it would convert into gas or vapor states. Okay. So, when further increasing temperature at a particular points, we can see that that liquid means would convert it into vapors, but we cannot distinguish liquid and vapor two phases. That particular point is critical points. So, that is also means that way matter changes, means solid to liquid, liquid to gas or vapors, and sometimes three different phases are present, sometimes two different phases are present, sometimes we are unable to distinguish gas or liquid, gas or liquid phases. So, depending upon the temperature pressures we are maintaining. So, okay. So, now we will discuss let us say any nanomaterials or materials we are preparing, it would arrange a particular way or orderly. So, here we have classified that three different way, maybe it present in amorphous state or amorphous phase. So, here there is no specific arrangements of atoms or ions or molecules which presents in that particular irregular arrangements. There is no regular arrangement. So, randomly distributed that atoms in that particular way. So, we can say that it is the solid in amorphous phase. Okay. So, when it is orderly arranged, though, then we can say it is single crystals or single crystalline materials. So, in that particular state of solid materials, the arrangements of atoms or molecules, ions, that is orderly present. So, then we can say it is crystallines. So, when it number of different type of crystals present in any solid, so then we can say it is a polycrystalline material. So, here's crystallines, this is also crystalline, but a different type of crystals, single crystals are present in that particular crystalline solids. So, we can say it is a polycrystalline materials. Okay. So, now a single crystals, depending upon their order of arrangements, it has many applications, and depending upon their means order of arrangements, different type of physical properties depending upon their applications, means dielectric, electricals, diodes, solar cells, many applications are there. So, there is particular optical property, magnetic property, those are used for that particular application. So, if we are able to prepare that way of material, so then we can use that applications, and that device or systems will operate or give more efficient way or better way that we can operate and get the performance better. So, also thermal property also that can be used for that particular materials. Okay. So, now here's a few examples of single crystals that we can say. I said it is infinitely long arrangements of atoms or molecules with a certain symmetry. So, hence we prepare a particular crystals or materials, that may be any metals or metal oxide elements we can use to prepare that materials. It is a single crystal. So, means the arrangements of atoms or molecules, that may be means orderly arrangement. So, here this is, you can see this is the shape. So, here one transparent Al2O3 alumina, that is sapphires. So, that is a gemstones, it is a single crystal. So, it is here, if you look into that, or here if you analyze in terms of atoms or single, the arrangements of atoms are orderly arranged. So, next is the polycrystalline. So, here I said, so here a number of different crystals that present. So, here there is some grain boundary is present. So, each orientations of that crystals, there would be different way. So, all are not regular way. So, there is some crystal boundary is also present. So, these types of materials. So, here's one example. So, means you can see here, this is also alumina. So, here's that materials, once we prepare the materials in a single crystals or polycrystalline. So, I said single crystal, it is transparent. So, it's has that type of optical properties. When it is in polycrystallines, so it is not single crystal. So, then its property it changes also, its mechanicals, opticals, that materials property also would be different, okay, from that single crystal to polycrystalline material. So, here Al2 alumina ceramics. So, when it is heated up at high temperature, so it is the materials, it is molecules or atoms that is distributed in this particular ceramic powder. So, or these materials, it is means when it is heated up high temperatures, only then this type of polycrystalline materials would be prepared, or that would be forms. And here if you notice very clearly, so then many small randomly oriented crystals that is present, and when it is forms at high temperature, that would be composed or fused when that materials is formed. Okay. So, here is also in amorphous materials, there is some means in polycrystalline materials, I said there is some grain boundary is present, means one particular way of arrangements of crystals to another. So, there is some grain boundary is present in polycrystalline material, but in case of the amorphous materials, so there is that type of grain boundaries is absent. Okay. So, that would not present. So, randomly the atoms or molecules will be distributed. So, here's one example you can see. So, a thin film of alumina oxide. So, aluminum oxide that is deposited here. So, that is in particular electricals device. So, there's it has some particular property, that is optical properties. For that particular property to get that type of amorphous aluminum oxides, that was required, and that was deposited in this particular device when it was synthesized or it was layered over that particular surface, and that is in the form of amorphous states. Okay. So, there are some other examples also. I said few materials may be amorphous or few materials may be crystalline. So, sometimes here in the previous examples we have showed that is made of aluminum oxide Al2O3 at different states. So, amorphous and crystalline phase, ceramics and sapphires, that is transparent alumina, that is in amorphous state, that I said. So, now if we look into carbons elements, that is with the carbons also we can make a different type of amorphous carbons allotropes. So, that may be diamonds or graphite type of materials. So, these are the materials also we can prepare with the help of carbons by considering a particular method of preparation. So, it also considers a different type of way of arrangements of atoms. So, in case of the diamonds, it is transparent, colorless and very hard materials, the properties of that material. So, here in this, if we look into that, so there you can see that each carbon atoms, it is made of carbons, and each carbon atom that is bonded with 4 other carbon atoms, and 4 carbon atom that is arranged in tetrahedral way of arrangements, and it is a 3D lattice, 3 dimensional lattice, rigid lattice. When that diamond is formed, later the structures I will discuss. There is covalent bond formation is there between one carbon to another carbon. So, that bonds, that is the covalent bond formations is there, therefore, it is also poor conductors, means since means tetrahedrals and 4 carbon atoms are arranged or tetrahedrals way of arrangements, and the bonds each carbons is covalent bonds. So, there is therefore, it is a poor conductor of electricity. Okay. So, similarly in case of graphite also made of carbon. So, that is soft, black and opaque, where diamond was transparent, colorless and very hard. So, here's means due to their different way of arrangement, means when they form a particular crystals or unit cells. So, then their arrangements, carbon arrangements, in case of the graphite 3 carbon atoms that arranged in the hexagonal layers. So, in case of the graphites, it forms hexagonal layers of carbons atoms, 3 carbon atoms, and that layers hexagonal type of layer formation is there. So, and also some free electrons movements or pi electrons bond is there in case of graphites when they are formations of carbon to carbon bonds. So, therefore, they can conduct electricity, means conduct electrons. So, are good conductor of electricity, whereas in case of the diamonds it was the poor conductors of electricity. In case of the graphites, due to their arrangements of atoms, different forms or different shapes, so they are sometimes they are good conductor, bad conductors. So, in case of the diamonds, you can see here each carbon atoms that is bonded with other 4 carbons atoms. So, this is carbons and this is also carbons. So, they are each carbon atom bonded with other carbon. So, in tetrahedral forms. So, 3D lattice, and therefore, due to their this type of arrangements they are hard. Okay. And so also covalent bond formations is there, therefore, they are not good electrical conductor. Okay. And in case of the this is graphite. So, here also this is carbon atoms. So, carbon atoms that is arranged in hexagonals phase or states, their formation is there. This is one layer, this is another layers. So, that layer by layers that formations is there, although that covalent bond formation is there, but that bond, the binding force in between these 2 bonds is very weak and they can conduct electricity. Okay. So, now we will discuss about the arrangements of atoms in a particular crystals, lattice, unit cells when we talk about 2-dimensional, 3-dimensional lattice structure. So, then the arrangements of atoms. So, that the basic things. So, I think that is need to discuss. So, therefore, this is lattice, means here you can see this is the lattice. Here a regular arrangements of atoms or ions or points whatever in a particular crystals, that point is repeated periodically. So, here's one unit cells, another's, that way it's orderly, periodically, repeatedly they are arranged a particular directions, that may be x directions, y directions, or maybe x, y, z 3 directions. So, depending upon their directions or arrangements of that atoms or points. So, we can say it is one dimensional, 2 dimensional or 3 dimensional. So, depending upon order of arrangements of that particular atoms or points, we can say it is that way 3D lattice, 2D lattice or 1D lattice. Okay. So, next is the crystals. So, these crystals, that is also an atoms or group of atoms that are attached to each others in the lattice point. So, that is called crystals. Okay. So, that crystals also 3D arrangements of highly ordered atoms, ions or molecules. Suppose you have a solid. So, in that solids, if we consider that is a 3D arrangement, 3D structure. So, that atoms or molecules that is placed. So, that is orderly, highly orderly arranged of that particular atoms or molecules or ions. Okay. So, in that way they form that particular crystals. Okay. Next is the unit cells. So, this is unit cells. So, here in unit cells also it is a small group of repeating patterns of atomic structures. So, this is we can say unit cells. Here also these are the atoms. So, that are arranged in a particular way, that is small units. When the small unit is repeated, then it forms crystals or crystal structure or lattice that would forms, but this is the actually building block or the basic units for any crystal or lattice formations. Okay. So, that way we can say. So, these structures it has means depending upon the atom or ionic size or volume and total unit cells whatever that is, that would forms its volumes or structure also will vary, or depending upon that size of that ions or atoms. Okay. So, here the unit cells, whatever the unit cells we discuss. So, here I said the atoms that would be arranged in a particular order. So, here these unit cells we can divide into two different category. One is primitive unit cells and another one is non-primitive unit cells. So, in primitive unit cell, that is simple cubic arrangements of atoms. So, here you can see this is primitive unit cells. So, here each corners or points you can see here atoms are present. Okay. So, that is simple cubics. So, lattice points only at its vertices. So, these are called vertices. So, here's only lattice points or atoms that would be arranged. So, it calls primitive type of unit cells. If it is not that type, little bit difference, means the atoms apart from these vertices, if some other points or locations atoms are present, that is non-primitive unit cells. Okay. So, here's body centers, face centers, a end centers, edge centers. These four different types of also non-primitive unit cells we can categorize. Here BCC, all vertices atoms are present, and at the centers of these unit cells another atoms are also present, or ions molecules present. So, then we can say it is body centers and face centers. Each vertices you can say that atoms are present 8 different points, and at the same times a particular face, this type of face centers. So, there also some atoms or points are present, and that also to make this type of face centered lattice. So, that type means each vertices at the same time center of particular face atoms also will be present. Okay. And end centers means all vertices their atoms are present, and then at the bottoms and top layers the centers that atoms will be present. So, then it is called end center. That way orderly means z directions, means you can consider that way one unit cells, another unit cells, 2, 3, 4, that way it would be combined, and then large crystals would forms. Okay. And edge centers, here's also all vertices points, you can say 8 points are there. So, there's 8 atoms are present, and after that sides, insides each sides also atoms are present. So, this type of also arrangements or crystals that is possible. So, unit cells. So, this type of is called edges centered unit cells. These are non-primitive unit cells. Okay. So, now we will discuss about the symmetry. Okay. So, symmetry, that is actually suppose you have a spherical systems or spherical geometry or circular geometry. So, if you rotate that with the help of particular axis, so after any angles if we rotate that, so after that rotation, so same structures if you are able to get. So, then there is some, we can say that means rotational symmetry is present, means similar structure, there is no changes of the order of atoms and no changes are there. So, similarly in case of the this is circular geometry we have taken. So, in that case, so means rotational symmetry is present. So, here in case of suppose you have a square geometry of cell or materials we have taken. So, this is its axis, if we rotate 45 degree, so clockwise or anti-clockwise direction. So, then there is no symmetry after 45 degree a rotation. So, both are different. So, against second rotations means second fold rotations means after 90 degree rotations. So, similar structures we are able to get. So, then we can say that suppose you have a square geometry. So, then two-fold symmetry or four-fold symmetry means after rotations of 180 degrees we can get similar type of structure. So, in case of square geometry. Okay. So, similarly we have a rectangular geometry. So, then there also initially the structure is a rectangle. So, here if we rotate 180 degree, so then after that similar structures we can get. So, this type of symmetry is present. Okay. So, here means 90 degree if we do rotation. So, for 90 degree or one fold 180 degree one fold rotations, and in case of the two fold or 180 degree rotations. So, we will get the similar structures one fold two fold means in one fold 180° if we rotate. So, then we will get the similar type of structures. Okay. So, now we will discuss about two dimensional crystal structures. Okay. So, there are 5 types of units lattice or Bravis lattice for case of two dimensional crystal structure. So, that we will discuss or that we will see means what are the different types of units lattice when it is the structure is 2D. This is called 2D. So, this is x and y. So, two dimensional crystal structure. So, in that case crystals, here's the 5 types of units or Bravis lattice are present. So, this is square types, this is rectangular types, centered rectangular types, this is hexagonal lattice and this is oblique lattice. So, the oblique lattice. So, these 5 different type of depending upon their distance between A, side distance A and B, and at the same times angles depending upon. So, if their A and B both are equals and theta equals to 90°. So, then this type of two dimensional square lattice formations is there, and rectangular lattice. So, whence A and B both are unequals and angle is 90°. So, then we can say it is rectangular types, and third type is A and B both are not equals and angles and 90° theta, and at the centers there is some lattice points is also present. So, then this we can say it is a centered rectangular lattice. And another hexagonal type of lattice, this is also hexagonal type of lattice. So, here A and B both are equals and theta more than 90°. So, that is 120°. So, in that case this type of arrangements of atoms we can say it is a hexagonal lattice, and also oblique lattice whence theta not equal to 120°, where A and B both are equals means this distance and this distance both are equals, but angles that is more than 120°. So, then we can see oblique lattice, the arrangements of 2D arrangements is oblique lattice. So, here's also same things. So, 5 different type of units or Bravis lattice. So, considering their distance between two atoms, a particular directions x, y, and at the same time angle between two sides. So, we can categorize that particular type of crystal arrangement. So, when it is 3 dimensional crystal structure formations is there. So, then we can have 14 different type of Bravis lattice. So, here's in case of the 3D lattice. So, I said when that atoms or ions will be arranged at particular points. So, this type of points 8 different locations it is lattice will forms, that is called primitive type of unit cells will forms. So, when the points are at vertices, so then we can see it is primitive type of unit cells. So, here triclinic, monoclinics, orthorhombic, tetragonals, cubics, trigonals, hexagonals, these 7 types of crystal systems are there, and with this each particular crystal systems may be 1, 2 or multiples type of others arrangements, means other than primitive cells the atoms arrangement should be different. Like this here in case of the this type of crystal system, when it is triclinic arrangements, so there it is primitive unit cells, then monoclinic. So, here also primitive unit cells is present like that. So, after that other means other than primitive unit cells there is base centered unit cell. So, this is base centered unit cell, this is primitive unit cells. So, in monoclinic type of crystal, so where these conditions for particular sites A, B, C will fulfills, at the same times angles different alpha, beta and gamma. So, if it is followed like that, so then these primitive and base centered cells also formation is there when monoclinic crystals formations is there. Similarly, orthorhombics, there is primitive, base centers, body centers, face centers. This type of 4 category also forms in all 4 type of orthorhombic crystals will follow this. Okay. So, similarly, tetragonals type of arrangements of atoms, here also primitives and body center type of 2 different type of tetragonals lattice arrangements is possible. Similarly, in case of the cubics, primitive unit cells is present, body centers and face centers. So, these 3 different type of arrangements is also possible, and in case of the tetragonals one particular type of arrangements that is present, and in case of the hexagonal, primitive type of arrangements is present in case of means hexagonal type of unit cells. Okay, so here's few examples are given. Each type of arrangements means when it is the cubic or body center or face centers. So then this type of means either copper, silver, sodium chlorides. So if we means these type of metals if we are prepared, so there's this type of means atomic arrangements is present. Similarly, here few examples are given each types or categories when a particular Bravis lattice or order of arrangements of unit cells or lattice is present. So then we can say it is that particular types. Okay. Here also few examples body centers cubes. So cesium chlorides. So this is cesium and this I think chloride. So this type of means 3-dimensional crystals. Here coordination number is 8. Okay. So in this particular way of structures. Okay. It is one example. Another one is sodium chloride, that is the face centered. So that is also coordination number 6 here. Okay, so here means few chloride atoms at the vertices and centers means edge centers. So here sodium ions are present. So that way that arrangements of the FCC types of crystals is present. In case of the diamonds I said if green one is also carbons, green one is also carbons, but each carbon atoms connected or bonded with some covalent bonds with other 4 carbon atoms, it this type of means arrangements is present. So, okay, tetrahedral coordinations present in this case of diamonds, that is FCC type of crystal formation is there. Next is the hexagonal type. So, hexagonal types of arrangements of the carbon atoms, here you can see hexagonal close packed structure. So, here 6 atoms in the vertices 1, 2, 3, 4, 5, 6 atoms in the vertices, and above this particular planes 3 atoms, here also 3 atoms are present and bottoms also 3 atoms are present. So, that way means bottoms top layers and that way means one particular atom is surrounded with the 12 other atoms, 6 in this particular layers, top layer 3, bottoms layer 3. This way means arrangements of atoms is called hexagonal type of geometry that may forms when carbons is arranged and prepared that graphite. So, this type of structure may forms. Okay. So, when we convert from one structure to another structure, there is some advantage disadvantage or means depending upon that particular property. Means when suppose we have a BCC structures of irons. So, when irons at low temperatures, so that may form BCC type of structure. So, here's the density or atomic occupancy is 68% when it is BCC structure at low temperature. When we heated up that irons, so then it changes its crystalline structures, means BCC to BCC FCC mixtures and 912 degrees centigrade. When it is at 1000 degrees centigrade, it converted into FCC type of structure. So, low temperature it is BCC, at high temperature FCC structure. So, as a result what would happen? So, a particular when this arrangement to this arrangement it is changes. So, then atom occupancy means initially when it was BCC crystal it was 68% and when it is FCC type of crystals, so then atomic occupancy increased, means density is increased 74%. So, means when it is BCC density is high, when it is FCC density is high atomic density, when it is BCC atomic density is low compared to that. So, therefore, that particular type of property, so we can use or apply for a particular system. So, when it is useful, when low density or high density of that irons is used for a particular applications. Okay. So, here in two different type of BCC type of crystals and FCC type of crystals. In case of the FCC type of crystals, so there is no gaps in between two atoms. However, when it is FCC type of crystals, so there is some gaps is present. Okay. So, as a result that is means when it is heated up, so then the atoms may be vibrates when it is BCC crystals, means they are not interconnected. So, but here it is interconnected. So, depending upon that their ductile properties also will change. In case of the FCC materials, it has been observed they have more ductiles, they are FCC type of metals, they are more ductiles than BCC type of metals or that type of arrangements. Okay. So, here also in one graph also you can see, means depending upon means their particular order of arrangements of the crystals, their property also will change. So, when a particular materials, so here one low carbon steel has been shown, it is at high temperature it shows BCC, and it is when it is high temperature and low temperature it is their means their arrangements is like this, and FCC means with respect to their changes of temperatures, ductile property and brittle property, that is invariants. Okay. So, no ductiles and no brittles at low temperatures, means in case of this particulars means carbon steel. So, it would follow like this. Okay. If we this is high temperature to low temperature, so is brittle means when it is high temperature ductile property is there, when it is low temperatures this type of property may vary, but in case of the low ductility method it would follow like this, and when it is high ductility FCC type of crystals it is follow this. Okay. So, both are same, but invariant of temperature, means whether it is low temperature or high temperature, that would not changes too much, means ductile property or brittle, that is also property of that material. So, when that type of particular crystal is present, so in few cases it is changes like this way, in few cases it is not changes or it is invariant. Okay. So, here also few examples are given. So, particular FCC, BCC or ACC, ACP type of crystals or lattice. So, here's few metals that may at a particular room temperature, so they may follow or they may arrange their atoms like this way, and they give a particular type of structures. Okay. So, now crystallographic directions, that is expressed in terms of third brackets, and if it is let us say this directions it is 100, if it is this directions it is 010, if it is this directions z directions or c directions, so it is 001. That way we can crystallographic directions we can used, we can express that way, that is the actually the directions indicate actually the smallest length of unit vectors. Okay. And then Miller indices also, that also we have studied. So, Miller indices, that is expressed in terms of round brackets. So, it is also means suppose a particular plane is present, a crystal's lattice plane. So, how we can express that, means in which directions it is present. So, that is also expressed in terms of Miller indices, means depending upon this particular points locations. So, we can say that that particular means here's this is one type of planes, this is another type of planes, this is another type of planes. So, all three different type of planes considering 100, 110, 11, that way it is expressed. So, here's let us say intercept of on A, B, C, three different axes of the unit cells, we can express it has particular dimensions, maybe let us say that intercept is 0.2, 0.4 and 0.4 nanometers, this and this dimensions, each intercept is 0.2 nanometer, 0.4 and 0.4 nanometer, and axial length is that is 0.8, 0.4 and 0.4 nanometers. So, the ratio of this means 0.2 divided by 0.8, 0.2 divided by 0.8, so that would give equals to 1 by 4. Okay. Similarly, 0.4 divided by 0.4, so we will get 1. Okay. So, similarly in case of the C axis, so 0.4 divided by 0.4, so we will get 1. Okay. So, inverse of this, that would get 411. So, if we inverse this we will get 411. So, that indicate a particular planes. Okay. So, that is actually the planes of Miller indices of this particular planes of that particular lattice is present. So, locations and directions is expressed of that particular planes. Okay. So, now bonding, so already we know this is the basic thing. So, means there are different type of bondings are present, covalent, ionics, these are present, covalent bonds, ionic bonds, metallic bonds, mixed bond, secondary bonds is also present. So, these are the things depending upon the materials we are preparing. So, in case of the this type of hydrocarbons or gaseous elements, this type of bonds are present, ionic bonds are present here in case of the metallic bonds, and there are few metals means ionic non-ionic both are present, and secondary when let us say C2H4, that is in high temperature it is gas. When we down the temperatures, the gas will be converted into liquid and then solidifications or solitude forms. So, in that case also some bond formations is there when they are in solids, that is called secondary bonds. Okay. Sometimes these covalent bonds that we know already we studied that. So, sharing of valence electrons between two atoms and formations of bonds, this type of, so covalent natures of bond formations is there, few examples are there. Okay. So, in case of the ionics also, so transfer of electrons from here to here, so ion formations is there and they stay together and forms that type of crystals, sodium chloride crystals or these crystals, and exist as that way of material sodium chlorides, and their ionic natures both cations and anions are present. Similarly, in case of the metals also metallic bonds are present, and this type of bonds actually electrostatic interaction between positive ions and free electrons is present. When as a result they are good conductors, sometimes they are pass when we pass electricity through this, so free electrons can move and then that particular metals may be conductors. Okay. So, another type is the mixed type of bond is present, means neither it is ionic, neither it is covalent 100%. So, let us say silicons we have, it is 100% covalent natures, germanium that is also 100%, 0% ionic natures. So, in case of the zinc oxides if we are prepared, so it is covalent 38%, 62% ionic in natures, and in case of the CDS cadmium sulphide, so 69% ionic in natures and 31% covalent in natures. Similar GAS, so 31% ionic in nature, 69% covalent in nature. So, depending upon, so the materials we are preparing, it has particular bonds and then bond formations, covalents, ionics or both the types of presents, and if we apply or prepare that materials considering that particular metal oxides, metal sulfides, so then depending upon applications it would will get that particular properties in that particular device or applications where we are using that. Okay. So, today is up to this. Thank you.